could measure. And I'm not looking for like specific examples or specific units, but like properties that you could measure. So what's a property you could measure? Time. What else? I heard distance. Keep going. Volume. What else? One? Mass. What else? Speed. Keep going. Density. If you haven't offered me one, come up with one. Say again. Light. Did I hear light or length? Length I'm going to count into distance. I'll also put luminosity here though because I said light in anyway. Temperature. What else? Acceleration. Velocity. Momentum. Inertia is mass, so I'm going to put that one here. Anything else? What else could you measure? Absorption. Viscosity. Force. Strength. I'm going to count that as force. Anything else? Energy. Any more? So I've listed them into two different columns. The columns that I've formed are based on whether or not that unit is scalar or vector. So all the ones in this column are scalar units, meaning they just have a magnitude to them. Over here we've got our vector units, meaning that when these units are stated, not only do they have magnitude, but they also have direction. So these are units with only magnitude. And these are units with magnitude and direction. With magnitude and direction. Okay. And in case you are someone who might have difficulty remembering that vector units are units that have both magnitude and direction, one of the ways that you can try to remember that
It's a mathematical term. Quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check. Orangutan! Oh yes! Finest life for orangutan.
every science teacher, everybody else.
Oh,
All right. So, if you do have any difficulty remembering that vector units are ones that have both magnitude and direction, I refer you back to Despicable Me. All right. Say again. The specific units that we're going to be interested in today are acceleration, velocity, distance, speed, and I didn't get it on here, displacement. So we're just going to start out by talking about one-dimensional motion and how these 5 different values are related to each other. So one-dimensional motion. All right, to start, we're just going to define each of these different values or different properties. Distance is simply the length of a path taken between two locations. distance, length of a path taken between two locations. The next one, displacement, is the change in position between two locations. And I should specify the change in position in a certain direction between two positions. The change in position in a certain direction between two locations. So just working with the difference between those two. So then expanding from these two terms, we're going to go ahead and go to speed and velocity. So speed is the average rate of change in position over time. Average rate of change in position over time. Whereas velocity is the rate of change in position in a specific direction. In position in a specific direction. And since we've got definitions, we're going to go ahead and get our fifth one in here, acceleration, which is the change in rate of change in velocity over time. A rate of change in velocity over time. All right, questions about any of those five definitions or differentiating between them? So far, so good? All right, then what we're going to do is we're going to plot some motion. I'm going to get up and move back and forth, and we're going to turn that into a distance and a displacement. So to start, get axes here, displacement and time. I'm going to start right here at 0 because I said I started at 0 location. What was the first thing I did? What was the first thing I did? Yeah, I walked towards the back of the classroom. How far did I go? 2 squares. And how long did it take me? 4 seconds. All right. So 1, 2, 1, 2, 3, 4. Don't tell your math teachers we're not drawing a scale. We're really not even worrying if our lines are completely straight. All right. So we've got that. Then what? Then what? Stood there for 2 seconds. How do I show that? Horizontal line. All right, so another 2 seconds. Going to have a horizontal line here. Then what? What did I do next? Went backwards. How far? 3. Yep. So I'm going to come back, and it took me 6 seconds to do so. 3, 4, 5, 6. So I'm going to be going to here. Something like that. And then what? Pause for 2 seconds. All right. So like that. Another flat line. So that's our displacement versus time graph. On displacement versus time graph, you can tell my exact location at any given point in time throughout that course. Okay? So indicates exact location. All right, now let's try drawing the same motion, but on a distance versus time graph. What do you project is going to be the biggest difference? Say again, James? Right, there won't be a negative slope for any of the lines. Why not? Right, you can't have negative direction since distance doesn't talk about direction. Distance can only be positive because it's a scalar value. So I'm going to start out exactly the same. 1, 2, let's get in 6 seconds here. It's going to look pretty much identical for the first 8 seconds. But then instead of going back, I'm going to go up another 3. And 1, 2, 3, 4, 5, 6, something like that. Now I'm increasing and then I'm going to stop there. So with the distance versus time graph, I can't show which way I went or where I am exactly. I just can show how far I've gone total. Questions about the difference between the two? Okay. Additional information that we can find from displacement or distance versus time graph relies on the slope of that graph. How do I calculate slope? Easy question. How do I calculate slope? Rise over run. So m is rise over run. In this case, rise, or change in y, is displacement. And run, or change in x, is change in time. Did we define anything as a change in position over a change in time? Did we define it? Yeah, what? Speed and velocity. But since we know that this one has direction implicated in it because it can be positive or negative, that means this has to be velocity. Similarly, you could talk about distance over time, and that could give you speed. So displacement gives us velocity, distance gives us speed. So the slope of this graph, speed, and this one, slope, is velocity. Okay, so when we've got a positive slope, we're moving forward. When we've got zero slope, we're stopped because we have zero velocity. When we have a negative slope, we're moving backwards because we have a negative velocity. So far, so good? Okay. Then let's go ahead and take a look at the next version of these graphs, velocity and speed versus time. All right, so for the speed or velocity versus time graph, how do we want to start that one? How do we want to start a velocity versus time graph for that same motion? Okay, so the slope of this one? Okay, yes, the slope of this one will be my y coordinate. So some positive value, probably around a half. So I'm going to start here, and where do I go from there? Horizontal. Is my velocity changing for the first 4 seconds? No, I walked at a constant rate for those first 4 seconds, so I have a constant rate for the first 4 seconds. Then what happened? I stopped. So I'm going to drop to 0. I'm going to stay stopped for a couple seconds. Then what? Say again? Then I went backwards. How am I going to show that? Right, I'm going to need a negative value here. So I'm going to have a negative velocity for a while, and then back to a 0 velocity when I stop again. Okay? Comparing the velocity and the speed versus time graphs. How is the speed versus time graph going to be different? Again, it's not going to have negatives because speed is a scalar value and doesn't care about direction. Since I don't have direction, I can't show negative or positive. It's always just going to be positive. So again, I start out with a constant speed because my speed is a constant slope. Then I stop for a while. Then I pick up my speed again and go right back to the same speed I was at. And then I stop again. Questions to there? Is everybody good with how I devised my four graphs? Like where they came from? Okay. Well, then let's keep this trend going. Velocity versus time. If I am looking at the individual spots here, I can tell exactly how fast I'm going at any given time just by looking at the graph. But additionally, I can take the slope. Again, slope being rise over run. In this case, rise giving me change in velocity, divided by run being change in time. Did I define anything earlier as being change in velocity over change in time? Acceleration. So I've got, just from my slope equation, change in velocity over change in time is acceleration. Therefore, slope of a velocity versus time graph is acceleration. Slope is acceleration. Similarly, we can talk about the slope of a speed versus time graph being acceleration. However, that's not as reliable because we can't tell if we're moving forwards or backwards with the speed versus time graph. So we don't really know what kind of acceleration we're experiencing. We can just tell the absolute value of the acceleration. So slope is the absolute value of the acceleration. And I need to actually get that onto the screen. All right, questions about those four? Okay, then I want to see if you guys can plot a different kind of motion on your own. I'm going to take a rubber band ball. I'm just going to toss it into the air. Catch it. We're only interested in the time it leaves my hand to the time it comes back to my hand. Take a moment and draw just a displacement versus time graph for the ball leaving my hand, going up a meter, and coming back to my hand. Yeah. What should my graph look like? Goes up and comes down. All right. So drawing something like that. I've got it curved. Should it be straight lines? So curved or straight? What do you think? It is displacement. So just displacement, so straight. Why curved? Okay. You tried. Anybody else? Why curved or why straight? Stefano. Okay, I would agree with that. So if we watch the ball as it leaves my hand, right after it leaves my hand, it's moving faster than when it's up here, right? Because it stalls out and stops at the top. So that means that it's not just going to go at a constant speed, stop, and then come back down to constant speed. It's slowing down, stopped, speeding up, right? So it can't be straight lines because straight lines indicate that it moved at the same speed the whole time. It didn't. The changing slope of a curve indicates that it's slowing down and the speed or the velocity is continuously changing at every instant in time, right up until the point where it stops and then starts changing again as it's coming back down. Everybody good with the fact that it's a curve? Okay. Next one. What's the velocity versus time graph look like? What'd you guys decide? A straight line with a negative slope that intersects at 0. Just stop there and then keep going. Okay? Anybody have something else that they drew? So you had more of a curve. Okay? Nothing? Okay. Others. So a few things. First of all, I like that this starts in the positive. I like that it starts in the negative. I like that it reaches 0. Because this slope is positive. Then it goes to 0. Then this slope is negative. So we have a positive slope, or a positive velocity, 0, and then negative velocity. So that trend is definitely right. Now, the question then is, should it be straight or should it be curved? In order to answer that, we've got to think a little bit about what does the slope of a velocity versus time graph tell us? Well, from the previous problem, we know that it tells us what? Slope is acceleration. What is causing the acceleration of the ball or rubber bands the entire time? Gravity. Is gravity changing at any point in time? No. So the slope of the velocity versus time graph must be constant in this case because the acceleration due to gravity is constant. So yes, I like this line. All right, and then lastly, we have our acceleration versus time graph, which we understand is the slope of this line. Well, that's a negative constant value. Negative constant value. Questions about any of those three graphs? Okay, so we mentioned that the slope of each one could bring us down to the next one. The slope of displacement versus time brings us to velocity. Slope of velocity versus time brings us to acceleration. But we can actually also move back the other direction simply by finding the area underneath the curve here. So if I were to take my acceleration versus time graph and I were to find how much area this is, how would I calculate that? Base times height. It's a rectangle. So my base, time, times my height, my acceleration, is equal to something. Well, if we take a look up here, change in time multiplied up here, change in time times acceleration has to be what? My velocity. Therefore, the area underneath an acceleration versus time graph must be the change in velocity. Versus t is change in velocity. Couple of things there. First of all, if you didn't catch on, a triangle is change. So it's the Greek letter delta, and it just means change. So is change in velocity. Second thing, this is the change in the velocity, not what the new velocity is. So acceleration versus time graph for something that's going from 0 to 20, or sorry, from 20 meters per second to 0 meters per second, would look the same as something going from 100 meters per second to 80 meters per second. It's just showing us the change in the velocity, not what the final velocity is. Good? Okay. And if I move up here, I can do the same idea. I could find the area under this curve, or the area here. And area under this curve, well, velocity times time. If I look back that one, the area under this curve is then displacement. Area under the curve is displacement. They would in this case. And that should make sense because if I take the ball and I toss it back into the air, it starts and ends in the exact same location. So if I took it and I tossed it into the air and paused it up here, then I'd just have this area and I can figure out how high I threw it. But if I account for the fact that it then comes back to my hand, well, it started in the same spot as it ended. Displacement would then be 0, and yes, they would cancel each other out. Okay. Lastly, displacement versus time, we're not going to bother finding area under there. So one of the things we can notice is that this is actually a chain, displacement, velocity, acceleration. Moving down the chain, you're using slope, Slope slides you down. Moving up the chain, you'd use area. Anybody in here already take pre-calc or calc? Everybody else, plug your ears. Derivatives and integrals, look familiar? So derivative of this one is the next, derivative of this one is the next, integral of this one is back up the chain, integral here is displacement versus time. Literally why Newton invented calculus, because of that relationship. All right, everybody else, you can unplug your ears. Questions about any of these three? Okay. Then the next thing I want us to take a look at is recognizing when something has a positive velocity or a positive acceleration and vice versa. So we can look at one of these pieces of the graph. So we started out moving quickly. We got slower and slower and slower and slower and slower until it stopped, right? Positive velocity, what would be the sign of the acceleration for this graph? Negative. We can either know it's negative because, hey, look, we drew a negative one down here, or we know that the slope is negative, and therefore the acceleration is negative. So just because we're speeding up doesn't mean that we have to have a positive acceleration. Just because we're slowing down doesn't mean we need to have a negative acceleration. What actually matters is how the acceleration and the velocity's sign compare. If the sign of the velocity is the same as the sign of the acceleration, you're going to get faster. If they're opposites, you're going to get slower. If the sign of the acceleration and velocity are the same, the object speeds up. If the sign of the acceleration and velocity are the opposites, the object slows down. Questions pertaining to that idea?